Hi everyone. I've actually been working on the Atlantic Overturning Circulation since the early 90s when I started my postdoc at the Institute für Meereskunde in Kiel. And I want to give a short overview of some of the important current findings. And I want to just start with this overview diagram of what Wally Broecker has dubbed the global conveyor belt. This is a highly simplified picture of what the overturning circulation or thermohaline circulation of the ocean looks like. It's called thermohaline because it is driven by temperature and salinity differences which affect the density of the ocean. And so the other component of the large-scale ocean circulation is the wind-driven circulation. This is mostly at least thermohaline. And you can see when you look at the North Atlantic that there's this red band. This is warm surface currents moving north. And then in orange, you see these sinking regions where the deep water formation occurs. And from there, this blue band, this is the North Atlantic deep water, is returning south. And this obviously works like a central heating system with warm water moving towards the Northern Atlantic, cold water moving back out, and a lot of heat is left behind and given off at the surface to the atmosphere, which is the reason why this region in the Northern Atlantic, especially downwind on our side, the European side, is warmer than, for example, the North Pacific, which does not have such an overturning circulation. The first evidence that this system can change comes from paleoclimate, and I want to just give a snapshot of the last 400,000 years here from this very nice study by Andre and Victor, showing that we can actually reproduce the ice age cycles of the last 400,000 years in a climate model, in their climate 2 model. The driving force here are the cycles of the Earth orbit, the Milankovitch cycles, as you hopefully know, shown at the top. In the middle panel, you see the sea level changes. The black dashed line is the data, and the blue and purple lines are two model versions with different parameter settings. And you can see that between the ice ages and the interglacials, there is very big sea level changes of the order of 120 meters global sea level change. And you can also see that the model reproduces these sea level changes very well. Why do we show sea level? Of course, why? Because the ice ages are called ice ages because of the buildup of huge continental ice masses. And the changes in sea level are a direct reflection of the buildup of ice. The sea level at the height of the ice ages was more than 100 meters lower because so much ice was lying around on the continents, which was missing from the oceans. At the bottom is the carbon dioxide changes, which act as a feedback there. And I think Andre and Victor can be proud that they are able to reproduce these CO2 changes, because this is a very tricky part. It's the carbon cycle, and to get this right in a climate model is not easy because it involves a lot of biology as well as physics. Now, I'm talking about the ice ages because the evidence for instability in the ocean circulation comes from the ice ages. It was coming out from the Greenland Ice Cores, and they showed these abrupt climate changes during the last ice age. This is a time span of 60,000 to 10,000 years ago. So we see the second half of the last ice age and the increase into the Holocene at the very end there of this diagram. And the blue line is the Greenland Ice Core record, and it shows these funny spikes that are numbered here. They are sudden warming events, so-called Dansgaard-Oeschger events after Willy Dansgaard and Hans Oeschger the ice coring pioneers who described this. In green, superimposed is an ocean sediment time series, which is there just to show you that these funny spikes, these Dansgaard-Oeschger events, are not some fluke of the Greenland Ice Core. They are shown in many other types of data sets, not from ice cores, but from the ocean with different methods. They reproduce these changes. So they are clearly large-scale regional changes to the temperature. They're not global mean changes, though. They actually are in out of phase with the changes in Antarctica. So when it gets warm in Greenland, it gets cold in Antarctica and vice versa, which is one of the pieces of many pieces of evidence that suggests that ocean circulation changes are the cause of this, because the ocean circulation, as I showed earlier, transports a lot of heat along the entire length of the Atlantic from the south to the north. And if that increases, then the north gets warm and the south gets cold and vice versa. And so that's what we can call a flip-flop. And here is a schematic that we developed for how this flip-flop works. We think that these Dansgaard-Oeschger events start from a cold ice age state that is shown here. You can see in this diagram the northern hemisphere ice sheets. You can also see the sea ice, which is further south than in the present day climate, obviously because the ice age was a lot colder. And we can also see in the schematic ocean circulation that the sinking region where this deep water is forming is not up into the Nordic seas. The conveyor belt doesn't reach into the Nordic seas, but it stops further south of Iceland. And what we believe what happened during these abrupt Dansgaard-Oeschger events is this. The conveyor belt, the Atlantic overturning circulation, advanced further northward. It jumped kind of over the sill between Greenland, Iceland, and Scotland and warmed the Nordic seas, pushed the sea ice cover back, and that led to a lot extra heat release, and it was warming that whole region as shown in the contours there. That's from a model simulation with that Climate 2 model, which I already showed you the ice age cycles. Now, we think this was an unstable situation in glacial times, and so the system flipped back again after each Dansgaard-Oeschger event until a new one was triggered somewhat later, and so again another warming occurred. And this situation that is shown here, of course, without the big continental ice sheets on North America and Fennoscandia, that would be the situation that also prevails in the Holocene, with the conveyor belt reaching with the warm water from the Gulf Stream right into the Nordic seas off the coasts of Norway. Now, the first person who suggested that this could change again if it has changed in the Ice Age, if it was so unstable in the Ice Age, was Wally Broecker in this famous Nature article of 1987 called Unpleasant Surprises in the Greenhouse, where he said that we play Russian roulette with climate and no one knows what lies in the active chamber of the gun, so very colorful language. And he warned of sudden, abrupt, nonlinear changes in climate due to ocean circulation changes. And if we look at what the IPCC and just basically the climate science community has been predicting for the future for a long time, is typical here, a warming scenario from the fourth assessment report, 2007, very strong warming. But notably, the northern Atlantic has warmed the least, actually very little. This is just 0.5 degrees here in the center. And the reason why climate models predict a minimum of warming or even a cooling under global warming scenarios, the reason for that is the fact that in these climate models, the Atlantic overturning circulation slows down. If we look at what has really happened with our climate until now, we published this a few years ago, 2015, gosh, by now 5 years ago. Time flies when you get older. So what has happened to the temperature observations, this is just the standard NASA GISTEMP data since the beginning of the 20th century, is that practically the entire globe has warmed except for this cold blob in the North Atlantic, which is the only part on Earth that has actually cooled. There's a little bit in back in North Africa, but if you look closely into that, it's unreliable data. We don't believe that at all. But in the subpolar North Atlantic, the data are reliable. There's been a lot of shipping there, including research ships taking temperature measurements. So we know this cold blob in the Northern Atlantic is a real phenomenon. And it's the only place on Earth that has resisted global warming and has actually cooled. This is a recent figure by NASA made last year showing the observed temperature anomaly from the 5 years 2014 to 2018. And it's just another very striking image of the cold blob as it is now known. In that 2015 paper, we already suggested that the meltwater from Greenland could play a role in slowing down the overturning circulation. The mechanism is quite simple. If you add meltwater, you freshen the ocean. That means the salinity drops, and water that is less salty is less heavy, and so it's harder to sink down. The reason why the North Atlantic, there is deep water formation in the North Atlantic and not in the North Pacific is because the North Atlantic is saltier. And part of the reason why it's salty is actually because of that conveyor belt circulation, bringing salty water from the subtropics up to the north. That is this kind of chicken and egg situation, or it's simply a positive feedback. The stronger the ocean overturning circulation in the Atlantic, the more salty it is, and the more salty it is, the heavier the water is and the better it can sink and the stronger that overturning circulation. So it's a self-amplifying system, and we'll get back to that later because the Achilles heels of these self-amplifying systems are, of course, that they have a critical threshold where this self-amplification turns in the other direction. Now, our article was here on the cover of Nature Climate Change with this headline, Meltwater Weakens Ocean Circulation. A year later, the group from Klaus Böning from Kiel showed that in high resolution model simulations that Greenland meltwater starts having an impact on the Atlantic overturning circulation. And of course, we know that Greenland melting is accelerating. That's what the satellite data by NASA and others are showing. Now, we wanted to look more deeply into this, and we took this model from our colleagues from the Geophysical Fluid Dynamics Laboratory in Princeton that has this very beautiful ocean circulation. It's an extremely high quality global climate model, coupled ocean atmosphere. Here you are seeing only the ocean component and the sea surface temperatures. And you can see beautifully how the Gulf Stream comes here from Florida along the North American coast. It leaves the coast at Cape Hatteras, just like in reality, and breaks up into these meanders. This all looks very similar to what you would see in an animation of satellite images. Now, we used a CO2 doubling simulation from that climate model from Princeton and analyzed the sea surface temperature pattern that emerges from that CO2 increase. My PhD student at the time, Levke Cesar, did that. And the model simulation pattern looks like this. That is actually the deviation from the global mean sea surface temperature warming. So everything that is blue has warmed less than the global mean or cooled, and everything that is orange-red has warmed more than the global mean. And you see this peculiar dipole pattern here with, again, this the cooling south of Greenland. As I said, the core of that is actual cooling, but the outer rim is kind of just less warming than the global average. And here you see a strange warm anomaly along the North American East Coast. And in the model, these two things are actually connected because this warming also arises when you slow down the Atlantic overturning circulation. It has to do with the vorticity dynamics on a rotating sphere, that in that case, the Gulf Stream moves closer inshore. And you can see that very clearly in that model simulation. Here we have blue on the southern flank and red on the northern flank of the Gulf Stream. So it has simply shifted closer inshore. Lifke has looked at all the sea surface temperature data sets that are available to calculate trends since the late 19th, early 20th century. And this is what that picture looks like. It's of course much more fuzzy because we have not such high resolution ocean observations. That's clear. These are ship-borne measurements. And so it's a very fuzzy picture, but you can see as a dominant pattern in the North Atlantic, this strong dipole with cooling south of Greenland and this warm anomaly of the North American coast, which is actually well known to the fishermen and ocean institutions along the US East Coast, because it does have significant impact on fisheries as well, actually. And we call this a fingerprint pattern in our Nature paper from 2018. It's a fingerprint pattern for the weakening of the Atlantic overturning circulation. And we scaled this and came to the conclusion that this corresponds to about 15% weakening of the AMOC since the early 20th century, mostly actually since the middle 20th century. That's when it started to go really down. We actually made it, there was a nice article in the Washington Post when our Nature paper was published, which I quite like because it was amongst the most read. It's one of the examples where science news can actually compete with Trump news in the media. And so a little notice to editors, newspaper editors, people are interested in climate science. In the meantime, a number of research groups have made proxy reconstructions from sediment cores in different parts of the Atlantic with different methods and try to reconstruct the strength of the Atlantic meridional overturning circulation from the proxy data. Here's the list of the papers that have done that. And you can see how in these different proxy data, the overturning circulation has evolved, basically stable for more than a millennium, and then it started to go down. And in the 20th century, we reach a low point, which is probably the weakest overturning circulation in the Atlantic for at least a millennium, probably more. We believe, of course, that this is a consequence of global warming, because we understand the physics. We have the warming and the meltwater input, both weakening the deep water formation, which drives this conveyor belt circulation. The climate models have predicted that with global warming, and it is just another prediction from climate models coming true here. What effects does this weakening have? Probably everybody has heard about this Hollywood film, The Day After Tomorrow, where the overturning circulation breaks down suddenly within a matter of weeks, basically, and it causes a total, an ice age, basically. That, of course, is unrealistic, although this film actually has a lot of nice parts to it. And it's based on a real concern that the overturning circulation could break down. I'll get to that in a second, but first I want to show what effect a weakening already has. And there's this nice paper by Aurélie Duchesne from a few years back, where she analyzed the connection between heat waves in Europe and cold out in the Atlantic. And this is, at first, it seems paradox. If you have seen the Hollywood film, you think, how can a cold North Atlantic cause a heat wave in Europe rather than cold in Europe. But the reason is simply the air pressure anomaly that this cold blob causes, which is a low pressure anomaly, and you know, the airflow around the low is counterclockwise in the northern hemisphere, and it brings a southerly a wind from the south here into Europe, and this airflow then leads to heat in Europe. And this is was a clear case in the European heat wave of 2015, which I think prompted Duchesse to do this study. It was published in the year after that 2015 heat wave, which I remember really well, because there was this Paris Science Conference before the Paris Climate Summit, which led to the Paris Agreement. This conference was in June in Paris, and I was there, and it was really, really hot there. And it's also a thing that the German Weather Service, which I actually learned from a newspaper article in Süddeutsche Zeitung, that the German Weather Service routinely uses that for its seasonal forecast, that if it's very cold out in the subpolar Atlantic here, they expect a warmer summer in Germany. So that's one effect of the cold blob. Of course, that's after a 15% slowdown. If the circulation really breaks down altogether, this cold blob will expand and start to really affect Europe also with cold. Now to another effect of the AMOC decline, is a study by other colleagues from Britain, the effect on the storm track. They find there is an amplified storm activity here in this belt if the AMOC declines, and it's less stormy further up here in the Nordic seas. There are many more studies emerging on the effects of AMOC slowdown, and we're looking into that ourselves as well. Now I want to finish up with the question that gets always asked, are we approaching a dangerous tipping point where the Atlantic circulation could break down? Let's have a look what is happening. Where are we now? Again, in a climate historic perspective, here is the global mean temperature since the last glacial maximum. These studies were published a few years ago in Nature and Science, after decades of paleoclimate research have provided so many data points, sediment cores, ice cores, etc., that a meaningful global average temperature can be computed from them. And we see here the warming from the glacial into the Holocene, then here the Holocene warm period, after that the very slow cooling. Underneath that, of course, is a 23,000 years precession cycle of the Earth orbit. That is one of the Milankovitch cycles, the shortest one of those. And we certainly would not, for natural reasons, have had this warming. This warming here is the anthropogenic signal that we see at the end. We have already exceeded the Holocene warm period temperatures now, and we are on the way of catapulting ourselves way out of the Holocene. That is the entire experience of human civilization since we invented agriculture, started to build cities, etc. And the question, of course, is this massive warming that is also much faster than anything we see from climate history. What will it do? Could it lead to tipping points being crossed? That is a real concern. And there's quite a number of these tipping points. Here's a nice diagram made by Ricarda Winkelmann for this paper that we published with John in 2016 in Nature Climate Change, where we list the kind of uncertainty ranges for various tipping points. For the Atlantic circulation, you see here a kind of burning embers uncertainty starting from about 2.5, 3 degrees. There is this risk of the Atlantic Ocean circulation breaking down. There is several tipping points much closer to home, even within the Paris range. Antarctic ice loss, the Western Arctic ice sheet, Greenland tipping point could be even below 2 degrees, as the work by Reinhard Kahlo and Andrzej Ganopolski has shown, sea ice loss in the Arctic, etc. So there are many tipping points there, but what about the AMOC? Or, sorry, I forgot I had this nice slide. What is a tipping point is the question I want to first briefly discuss. So what is a tipping point? It has been defined in this review paper, Tipping Elements in the Earth Climate System, by Tim Lanton and co-authors, several of them from the Potsdam Institute. And basically it's defined as a threshold where a gradual change in a control parameter leads to a pretty sudden big change in the response. And does that apply to the AMOC? Yes, is the short answer. The basic idea has already been described in the 1960s. Henry Stommel, famous oceanographer, 1961, showed that the AMOC has this self-amplifying salinity feedback that I already mentioned. And this leads to a stability diagram which looks like that. If you look at the strength of the North Atlantic overturning circulation here as a function of the amount of fresh water that you dump into the Northern Atlantic. And so when we start here somewhere on this branch, present climate is probably already in this bistable regime here, and you add fresh water, then the circulation slowly gets a little bit weaker and weaker. But then this stability curve actually turns back on itself. That's where the tipping point is, that I call the Stommel bifurcation after Henry Stommel. And there's no more stable state with the Atlantic overturning circulation switched on. So it has to drop down to this stable branch where the circulation is off. And when you want to restart the circulation, it isn't enough to go back with the freshwater forcing to where you started. If you started here in this bistable regime, it will stay off. You have to go further back here up to this second bifurcation point, and then the system will jump up again to this upper branch. You can go through this with climate models. We've done that with Climate 2. I've done it when I was still in Kiel with the GFDL ocean, global ocean circulation model. Climate models can reproduce this stability behavior, even complex climate models. The big question, of course, is where are we here and how close are we to this bifurcation point? And the unfortunate answer to this is we don't really know. You will often read that IPCC says it is very unlikely that we pass a tipping point, but that just means the risk is less than 10%, which I would say, okay, that's still far too high to take this risk. Would you board a plane that has a 10% chance of crashing? I wouldn't. And I don't think we should push the Earth system to a point in this century where we have a 10% chance of collapsing the Atlantic overturning circulation. But also another issue is that there is evidence from a number of papers, one of them by Matthias Hofmann, for example, and this recent one by Leo et al., suggesting that many climate models systematically overestimate the stability of the system because of certain errors in the salinity distribution in the Atlantic, etc. And Leo and colleagues here fix the salinity errors, albeit with a flux adjustment, to make the Atlantic more realistic in accordance with data. And they found that if you do that, the Atlantic overturning gets much more sensitive and does collapse from an ordinary CO2 doubling scenario. Now, if that worries you too much, I have a reassurance here from the Tagesschau, the German main TV news, telling you the Gulf Stream will remain stable. Interestingly, when I saw this on the news, I thought, what's happening? And I did a bit of research, and there was no scientific publication behind this news. There was simply a workshop on this topic that was being held in Hamburg, and they had sent a film team to interview a scientist there. So to summarize this question of whether the AMOC is approaching a tipping point, my take on this is that in principle, we know there is a tipping point. As I said, Henry Stommel laid the theoretical groundwork. It's been reaffirmed again and again with climate models. The physical mechanism is understood. So yes, there is a tipping point. We also know now, I think it's emerging knowledge at least, and it's also said that in the last IPCC special report on the oceans, the IPCC for the first time has said that probably the overturning circulation is weakening indeed. I would certainly argue that it's very likely that the AMOC is weakening in response to global warming. We have this fingerprint pattern that looks exactly like the one produced by the predicted AMOC weakening in high resolution climate models. And so that means we're kind of moving in the direction of the tipping point, but we don't know how close this tipping point is. And that's because this is an inherently non-linear thing to have such a tipping point. That's the whole point of a tipping point, is that it's non-linear physics. And non-linear physics means the whole system depends sensitively on the exact conditions, like that salinity distribution in the Atlantic that I have already mentioned. And so nobody really knows how close is this tipping point. I personally don't find that reassuring to navigate into uncharted waters in the fog, and you know there are rocks underwater and you don't know where they are or whether you are close to one of these rocks. And that's why I think it's a classic case for the application of the precautionary principle. And it's another very strong reason to reduce our global greenhouse gas emissions to zero as fast as we possibly can manage. With that, I'm finished. And if you want to read more, here's some suggestions. And thank you very much for listening.